I would like to welcome John Martinis. He was born 1958 in Los Angeles, USA, PhD 1987 from the University of California. He is a professor at the University of California, Santa Barbara, and Chief Technology Officer at Qolab. And join me in welcoming Professor John Martinis.
Thank you. Thank you. Thank you. This is a great honor to speak to you today, and oh, what happened here? Back up. Oops. And great honor. As a graduate student, I joined John Clark's group because he was doing at the time some really fascinating experiments looking at quantum noise phenomenon in these electrical circuits. And that kind of combined my personal interests, a hobby in electronics, as well as a graduate student where you're fascinated by quantum mechanics and you want to do experiments to understand it better. So today I have an honor to talk about our collaboration, but what turned out to be my thesis at UC Berkeley, and then talk a little bit about the end, where it's led, give some examples where it's led in my career with some other nice experiments. I want to say in my career I've been really privileged to focus on physics instrumentation, to make these quantum devices in a variety of form. And what I learned a few years ago by going to Cambridge, that if you look at my scientific family tree, if you like, through John Clark and Cambridge, I have a very interesting sequence of graduate advisors who have done fantastic instrumentation and discovered a lot of physics from that instrumentation. So there was a real focus in John Clark's group to do that I appreciate. Also at UC Berkeley, of course, there's Ernest Lawrence building the cyclotron and building all these accelerators at Berkeley, and that contributed to my interest in exploring such scientific instrumentation and led to many interesting things here. So we've talked before about macroscopic variables obeying quantum mechanics. I'm going to say my personal view, what is actually kind of discomforting to physicists with quantum mechanics, is there's actually two propositions in quantum mechanics. One has to do with the wave nature of quantum mechanics, and of course described by the Schrödinger wave equation and the energy levels and things like that. But a second part has to do with observation and measuring of that quantum state. And physicists really feel, a lot of physicists feel that there are one too many propositions in that. It should only be one. That's how we think. Of course, it works in the real world. You can do things. But part of this discomfort, I think, is very well described in the Schrödinger cat paradox, where you have a microscopic decay of atom, which either kills the atom or not, depending on whether it decayed. And then before you open the box to observe it to measurement, the paradox is, will this living being, a macroscopic cat, can be described as a dead plus alive state. And of course, as discussed before, Professor Leggett discussed that, well, maybe quantum mechanics is such that macroscopic objects can't be in a quantum superposition. We need to look for experimental evidence that that could be the case. And again, he proposed these electrical circuits. Now, one of the things Leggett did that was very nice is he said this is distinct from showing that microscopic quantum mechanics can be observable at a macroscopic scale. A good example of this are crystals, where you have atoms, because of the microscopic physics, attached to each other, and they'll stack up in a regular way because of that. And if you grow them right, they can stack up to macroscopic distances. But it's still, you're looking at a macroscopic property of them stacking up in a very reproducible way. And this is such a magical phenomenon that in my home state of California, such crystals are thought of having magical healing powers. So it's truly an amazing phenomenon. Now, the same thing happens with superconductivity, where the superconductors can kind of stack up in the phase, so you can get large superconducting coherence and the like. And what, of course, we're doing is something looking very different. Will a macroscopic object obey quantum mechanics? For example, throwing a ball against the wall, and okay, one small period of time, it'll tunnel through. That can happen for real balls, but if you make an electrical circuit in the right way, you can show that. Let's talk about macroscopic variables to make sure we really understand that. A good example is a gas at a high temperature of some material. Everything removes from the surface. The atoms are flying around. Obviously, a very complicated state to describe. If you go before the solidification temperature, it then forms, let's say, a solid, maybe even a crystal. But now, if you want to describe the state of that system, you just describe the center of mass. And that's a much more simpler description of what's going on with the physics of that than when it's in a gas. Same thing for electrons in metal. There's some Fermi statistics you have to worry about, but you can have a think about a gas of electrons. When you cool it down, it turns out the electrons flowing in one direction and electrons flowing in exactly the other direction form these things called Cooper pairs with a net zero momentum, so that each Cooper pair has zero momentum, and then every Cooper pair can interact with every other Cooper pair through some condensation mechanisms with phonons. What's very nice about the superconducting state is there's a free parameter to the state, just like in the solid, having the center of mass being a free parameter called the phase. And if there's a change in phase over distance, that is equivalent to a current flowing through the wire. And as long as that current isn't too big, it's in the superconducting state. If its current's too big, it kind of starts looking like a normal metal. It breaks the Cooper pair. Okay, so you have to keep that. So what we do here is make a superconductor with a weak link, a barrier. Here, it's a very thin aluminum oxide. And then from the Josephson effect, the current that flows through it has a maximum value of a critical current, which we can tune for a few microamps in our devices with a sign behavior of the phase difference, as been discussed before. But here, everything is still classical. This phase is a classical variable in normal way that you describe superconducting devices. As we've discussed before, we're interested in the zero voltage state where it looks like a good superconductor. And then if you have too much current through that, it then goes into a normal state, voltage state, rolling down the well. And this transition is determined by going over or through a barrier that we've described here. And that barrier height goes to zero when I goes to I0. It goes as the 3½ powers as to how close it is to that. Now, from this kind of description, one of the first things we did in the experiment was really clearly write down what the physics is. And that's shown in the three formulas here. The important thing is at high temperature, classically, this is just a Boltzmann factor and Arrhenius law, something you study in chemistry and physics all the time. And it's dependent very sensitive on the delta U over KT ratio, okay? Then in the quantum regime, it could tunnel, again given by another formula that I've given here. There's also, we consider the third case because of the quantum noise, delta U over 1/2 h bar megaplasma. We thought that wouldn't happen, but the point is these three formulas are very distinct. And if we measure the parameters carefully, we can tell the difference and we can identify what the physics is. Now, I want to talk a little bit about this quantum tunneling. And as journalists talk to me because of the Nobel Prize, whenever I say, well, there's a wave function, it leaks on the barrier, they totally don't understand that. So there's, I think, a little bit more intuitive way to think about it. And that is nature it can be a nervous banker. Okay, and what nature can do is it could lend you some energy, but they're going to want to recall the loan, and bring back the energy a small time later, t, such that the energy times the time is equal to this Planck constant h bar, which Michel talked, is about 10 to minus 34 in natural units. So if you have to have small delta U's and small delta D's, but then you can still borrow and return the energy. Now, one of the nice things about thinking it that way is if you put in damping and friction, as Michel talked about, you can imagine that because of the friction that goes on during the tunneling event, you're going to have to borrow a little bit more energy to make sure you can overcome that. And that's why in the quantum formula, in the exponent, there's this factor having to do with dissipation. So you can strongly reduce quantum tunneling if you have dissipation, and you have to design your experiment around that. So here's the experiment, and what I'm going to say is when we first did the experiment, it was a total disaster. It didn't work, didn't make any sense. No surprise if you're experimentalists. And we just sat down and tried to understand what was going on. And one of the first things we realized is that microwaves, this is a microwave experiment, right? This is oscillating at about 5 or 10 gigahertz. And that microwaves at that frequency are in fact very sneaky. And you know that because you get cell phone transmission from outside way far away, even inside a building. It can penetrate in some way and do that. So we had to design the experiment to be really good shield for microwaves. And we did that using this particular design. We have the chip here on the right with the cross for the junctions, and then it's connected to what is a coaxial line, which is really well shielded. There's a cap on the end to make sure that that's good. And then furthermore, in that what's coax, we put in copper powder, which is very damping of these microwave radiation because it has a lot of surface area in it. And you can see we go in with the copper powder. We have this SMA connector at the end, which is a really good tight connector. And then the other two barrels on the left-hand side on the picture are further filters to make sure none of this energy goes in. In the center, we have another microwave connector to inject microwaves that you talked about. So the filter here is actually one of the most important things we figured out and measured carefully, and that's how we got the experiment to work. So how do we measure the parameters? This was very important. So on the left, I think we already talked about, we took the device, measured the switching times, switching rates at a variety of currents, okay, so that the frequency is slowly changing there. We put in a fixed frequency here, 4.9 gigahertz, and then you see an enhancement of the rate when the microwave drive of the particle in the well here is at the same frequency, resonant enhancement. Study that all the time in physics. So from the peak of that particular transition, we can get the oscillation frequency of the system, and from its width on the high side, we can get the damping of that. So with that, we have a basic parameter, the oscillation frequency, which we need to know. On the right, we now plot the raw data. This is of the gamma. We normalize that to the plasma frequency over 2 pi. It's the attempt frequency. Take the log, and because of the power law, 1 minus I over I0 to the 3/2 for the delta U, you take to the 2/3. And this is an Arrhenius-like kind of plot, where if your data is good, remember at the beginning it wasn't, but now it's good, it should be on a nice line, which is what we see with the points kind of in the center of the plot. Those particular points, this is really nice. If you extrapolate that back to the 0 on the vertical axis, that then gives you the critical current of the device. That's where delta 0 goes to 0. And you can do that at various temperatures to see that you get a consistent value of I0. You put in corrections to understand that properly. And then the interesting thing, as you get the lower and lower temperatures, it gets steeper and steeper. And then between about 25 and 19 millikelvin, it just doesn't change anymore. And again, that's an indication that you're seeing new physics. So the slope of this is kind of giving you an effective temperature of the device, scaling out the delta U that's in the formula. So this is something we call the escape temperature. And here it's a plot of the escape temperature versus the real temperature, and as described before, T escape equal T at high temperature, because this is all classical physics. That's what you expect. And then as you go to lower temperature, it begins to level off. Now, let me stop here for a second. The fact that it's leveling off doesn't necessarily mean you're seeing quantum tunneling. And that was the big insight we had in the beginning. How do you know it's not other physics? It could be noise getting injected somehow in your system, and that's what's causing you to level off. So you really have to think carefully about what the check experiments are. Okay, so the one check experiment, we already bit the good microwave filtering, and we knew everything there was okay. The second part is we could take the system with the critical current and lower it by putting a magnetic field parallel to the junction. So that brings the critical current down to about 1 microamp. The frequencies of the oscillations are then lower. And then now it's going to be classical, almost always classical, almost all the way down to the end. And those are the open circles. And you see that it goes below. And that kind of proves that we understand what the temperature of the system is good enough. Now, and then the last thing is it levels off. What does it level off to? And that's the little symbol on the left for MQT, and that's the prediction after measuring all the parameters. And you can see within experimental error bars, everything's okay there. So we think that's a really solid way to understand that this is working properly. And we worked along really hard to figure out how to numerically show that. Okay, now I want to talk about energy level quantization. And this slide is for the new students who are learning about quantum mechanics. And the problem is in quantum mechanics, it was first understood, kind of discovered through the Planck radiation law of, infrared spectrum, okay? And there, what happens is you assume that the energy levels are quantized and separated by h bar omega, but then you have to do a bunch of statistical mechanics calculation, which at the time is really kind of murky and mysterious and hard to understand, and then you can reproduce the data, which is really great. However, for a new student, you kind of get overwhelmed here. So what I want to show you is that with our new quantum devices that we can now make, which is kind of a child of all this work, you can directly measure photons. Okay, so this is an experiment I did with Sewoo Nam in the late 90s. Unfortunately, he died last year, but the experiment is really great. And what we do is we take a very small piece of superconductor at very low temperature, which has small heat capacity, and you operate it on the superconducting transition, so it's very sensitive, and then you connect it to a quantum limited squid amplifier we talked about before. And now what you can do is you can put a pulse of energy and see really, really small fine energy resolution. So you take what looks like a classical pulse of light, this is a laser light, 1556 nanometers, you make a small pulse of it, so that on average has a certain, there's a certain amount of energy, you attenuate that, and you put it onto the microcalorimeter, okay? And when that absorbs the energy, it turns it into heat, the temperature rises, and then it'll fall over some amount of time going back to equilibrium. Exactly what you expect for a fast thermometer. And on the upper right of my figure here, we'll show some time traces of that, where you see that the temperature goes up, that's the signal, and then it goes down over time. But if you look at it, there are these bands of the temperature profiles. And if you look at the peak and you histogram that, that's the data you have here. So you have discrete peaks in the energy of this pulse. Now, classically, you would expect one energy. But here you see a band of them, and those are all separated by Planck's constant times frequency. And this energy level quantization that you see is exactly what you're assuming in the Planck radiation law, but now you just directly see it coming out of your oscilloscope from a fancy detector where you can measure very, very small energies. And my hope is that future generations can look at this experiment and kind of get a better intuition about how this works. So that's why I'm introducing it here. And then here we have an energy level experiment that we talked about before, where we put on microwaves and we see an enhancement of the escape rate when the microwaves are resonant in a certain way. And this is really great. This is a qualitative way to show you that you have a unique signature of quantum mechanics. That's kind of the fundamental signature with energy level quantization. And that was really great, great to see. When I saw this come up on the oscilloscope, this was like the most exciting part of my graduate student career. So what do we have looking at this? We have a new way to make artificial atoms. Normally we have the periodic table. Now we can look at these electrical circuits. And what I learned here at the Nobel week is I was looking at the poster for the economics prize, and it described about propositional knowledge. And what happens is when you have this kind of knowledge, it's very fundamental knowledge of what you're looking at technologically. It allows you to make discovery after discovery after discovery because you can kind of generalize and really understand what's going on. And what I would say is in this experiment, we tried to go to the basics to really understand this. And because of that, over the last 40 years, everyone in the big field has been able to make huge progress on that. I do want to make a caveat, though, that to make this progress, nature has been very kind to us with stable junctions so that we can do high-quality experiments, but has given us little subtleties at the same time, so a lot of physicists have to be employed to make this all work. So that's a good combination, okay. So Clay, right after that, we did a very nice experiment where we actually measured this tunneling time. Okay, and how do we do that? Well, using the ball analogy, we make a ball that's squishy, okay? And it has some time dynamics that we can tune. And then we look what happens to the tunneling as we change the ball. Now, in this case, we have a junction at the end of what's called a coplanar waveguide. It's much more sophisticated engineering. Right next to the junction is something with a wave impedance, a wave resistance of 72 ohms. And then some distance away, we have a kind of a short on it that has a lower resistance that gives you more dissipation. And then we connect that with a string all the way up to room temperature so we can change the distance. Now, as we look at the escape rate on the right, at high temperature, is given by delta U over KT. It's more or less flat. But at low temperature, then you get a big change in the rate or in the time, as shown by the finger. At short times, it's looking at the short with a lot of dissipation on it, and that gives you longer tunneling times. And then when it's long, you aren't seeing that dissipation anymore. You're seeing the 72 ohms, and it goes down to different. And then in between, it kind of goes up and down. And what's happening is, at this tunneling time, in this case about 30 picosecond delay, what's happening is the system is tunneling before that tunneling event has a chance to go down to the line, interact with the M, and come back and interfere with itself. So this characteristic time here is telling you this particular tunneling time. It's a real physical quantity. I think it's very nice with an artificial atom you can measure that. I want to next talk about something we did at UC Santa Barbara in 2008 and 2009 with Andrew Cleland here is in the audience. We were making qubits at that point, and we connected a qubit to what's these resonator circuits. And what we did in this particular circuit is we can calibrate up the qubit. We can, on the bottom left curve, we can put the qubit off resonant, so it's not talking to the resonator, on resonant, having it talk, calibrate that up so that we can controllably transfer photons from the qubit to the resonator. And what's very nice here is we're able to generate these very complex states. For example, 0 plus 5 or 0 plus I3 plus 6. And we do this using the very beautiful protocol of Law and Eberle. But basically by doing these two calibrations, but now doing a series of 10 or 12 pulses that interact everything together, from a simple calibration, we could then create a much more complicated state. And you see in the top here in the theory, the experiment is very much similar. This is a pseudo probability distribution called the Wigner distribution, which tells you about the quantum state. And reason I'm showing you this is we went from a simple calibration to a complex state generation. And at that experiment, I really had much more confidence that we can build a complicated quantum computer sequence and get it to work. So it gave me a lot of confidence we were on the right track. And then finally, before I summarize, this is the quantum supremacy experiment I did at Google, where we showed that with the 53 qubit, we can make a very complicated sequence with thousands of total gates calibrated upright and show that the results we get is equivalent to what you expect from quantum mechanics. And what was interesting here is the power of this circuit comes from using a very large computational space. It's something physicists call Hilbert spaces, which is about 2 to the 53, so it's about 10 to the 16 states. So, you know, kind of in analogy to my thesis experiment, this was showing that macroscopic quantum computation also based quantum mechanics. So we pushed the knowledge of quantum mechanics even further. And it's nice, other groups have even extended this even further. And, you know, because we've done that, we think it should be possible to build a powerful quantum computer. We just have to figure out what are the useful algorithms and fit that in right. So here's a nice summary of graduate students in 1985, what we were building. Still a good microwave experiment, but then the kind of chips we're building in 2019. And the whole field has been developing this in a very sophisticated way. It's great. I'm really excited for the future. What I'm trying to do in my thesis is going from 2019 to, let's say, 10 years from now, 5-10 years from now, to build a useful quantum computer. We're going to have to make a technological jump in fabrication that I believe is going to be just as big as from 85 to, say, 2019. However, I think because we can now use the semiconductor industry to do that and make it in a more reliable way, I don't think it's going to take 35 years to get there. I think we can do it much faster. So that's what I'm trying to do with my company. So in the final slide here, I just want to summarize that. And as I said in the beginning, I wanted to study these devices to kind of learn about quantum mechanics, and I would say intuitively understand how quantum mechanics worked. And I would say that's what's happened in my career, and it's been a real pleasure to understand that. And just to review that, we have this nice experiment that shows photons, that shows energy level quantization directly, which is really nice. We now can understand that tunneling traversal time. We have these photon generators, complex generators, and then the quantum supremacy experiment, where I think the remarkable thing that I found there, this is a prediction from quantum mechanics, but experimentally, is that although quantum mechanics isn't perfect and you get errors into it, if you just measure the single and two-bit errors and then measure the errors of the whole complex system, the relation is given by high school probability statistics. And I think it's just amazing that quantum mechanics works in this way, where you can get complex calculations out of it, but on the other hand, the imperfections of it can be understood in a more simple way. So with that, thank you for your attention. It's been a real pleasure to talk to you about my journey. Thank you.
Very nice. Very nice. So thank you, Professor Martinis. This summarizes the 3 Nobel presentations for the Physics Prize, and let us all thank the speakers one final time. Oh, please come on stage. On stage.